This sample problem deals with conservation of angular momentum and also the concept of rotational kinetic energy. So we have a person, we'll say his name is Nate. He's standing on the center of a frictionless rotating platform with arms extended horizontally. So Nate's center is above the center of the platform. The platform itself is a disk and has a moment of inertia given 0.3 kilogram meters squared. Each of Nate's hands is 65 centimeters away from the axis of rotation, and Nate's body has a moment of inertia of 2.3 kilograms meters per squared. Separately, the masses in his hand, 3.2 kilogram mass, 3.2 kilogram mass in each hand, has a moment of inertia. That's not included in the 2.3 kilogram meters squared. These masses are at a distance of 65 centimeters from the rotation axis. And right now, the angular velocity of the platform, of Nate, of the masses, is 0.6 radians per second. Our task, calculate the total rotational kinetic energy, and then we're going to have Nate pull the two masses towards the axis of rotation until they're only 5 centimeters away. Nate will have a new moment of inertia for his body, 1.1 kilogram meters squared. We want to know the new rotational velocity. Perhaps you've seen ice skaters do a spin move where they move their arms towards the axis of rotation, and you see their angular velocity increases quite a bit. We're going to calculate that. And then we'll calculate the new total rotational kinetic energy and ask the question, what changed the rotational kinetic energy? What was the mechanism that caused that rotational kinetic energy to change? So first, the kinetic energy, rotational kinetic energy. I'm summarizing here the data from the description of the problem, making a little sketch of the situation. These little blobs are the masses in Nate's hands that are 65 centimeters away from the axis of rotation. To calculate kinetic energy, rotational kinetic energy, it's 1/2 I omega squared. For linear kinetic energy, it's 1/2 mv squared. In the rotational system, we use I, the moment of inertia, or some people call it the rotational inertia. That replaces the mass. And omega, the angular velocity, replaces v, the linear velocity. So we're moving from a linear kinetic energy calculation to a rotational kinetic energy calculation. Well, the I is made of 3 pieces. There are 3 parts of the system that contribute to I. We have the rotational moment of inertia, rotational inertia for the body of Nate. We have rotational inertia from the masses, the 2 masses that are in Nate's hands, and we have the rotational inertia of the platform. We're going to treat the masses in Nate's hands as point masses. We're not going to worry about the complication that these are extended objects. We're just going to take all the mass concentrated at a point. That rotational inertia calculation is mr squared. So the system has a rotational inertia, a moment of inertia, of 5.304 kilograms times meters squared. The kinetic energy then, 1/2 of the I times the I number times the square. And don't forget to square the omega, 0.6 radians per second. And pause this, pull out your calculator. As an intermediate number, I write down 4 significant figures, but when I write down the requested answer, I round it to just 3 significant figures, so 0.955 joules. Second question. Now we're going to let Nate pull the masses towards the axis of rotation. So in my sketch here, I'm drawing the masses closer to the axis of rotation. Now the arms are no longer extended for Nate, so his body's moment of inertia changes. I'm going to claim it's 1.1 kilogram meters squared. And we want to calculate the new rotational velocity. Can we use conservation of angular momentum? Well, in order to conserve angular momentum, we must have no external torque on the system. So that's going to mean no external forces. Nate's arms are applying force to these masses, but that's internal to the system. So yes, we don't have an external torque. All the action here is internal. There's no friction creating torque on the platform. So angular momentum is conserved. Angular momentum is calculated with the moment of inertia times the angular velocity. So we have two cases when the masses are extended in the arms. So that would be situation 1. And situation 2, when the masses have been pulled in towards the axis of rotation. And I omega, angular momentum, will be conserved. This multiplication quantity will be a constant. So let's delve into that. Well, we worked out previously the moment of inertia for a platform plus Nate plus the masses in the extended arms. So we have that rotational inertia. Then for I2, when the masses are pulled in, we've got a new rotational inertia for the Nate's body, and we have the masses at a different position. And we still have the platform of 0.3 kilograms meter squared. So that sums up on my calculator to 1.416 kilograms meter squared. And now I'm applying conservation of angular momentum. So I have an I times omega on the left, an I times omega on the right. And this omega 2 is the unknown, the new rotational velocity after Nate pulls the masses inward. And I came up with a rounded version, 2.25 radians per second now for the system. The platform is spinning at this rate, Nate's body is spinning at this rate, the masses are spinning at this rate. What is the new rotational kinetic energy? Well, we take 1/2 I omega squared again. The I is changed. Now we have the masses close to the axis of rotation. We have a new value for I. And we just found the new omega. Don't forget to square that omega. I come up with 3.57 joules for the rounded version for the new kinetic energy. You might notice that these are different. The angular momentum is constant. The rotational kinetic energy is not constant. It has changed. Initially, we had 0.955 joules of rotational kinetic energy. Now the system has 3.5 joules of rotational kinetic energy. The kinetic energy has increased. So why did that occur? Well, in order to get these masses closer to the axis of rotation, the hand is supplying a centripetal force to these masses as they move around in a circle. There's centripetal force on the masses. That's directed inward, and the masses have moved inward a distance from the extended arm position to only being 5 centimeters away from the axis of rotation. There has been motion. So Nate's hands have done work on the two masses. Basically, work is force times distance, but you have to be careful. You can only use this if the force is constant. If the force is constant as the object moves. So there has been work done on the masses by Nate's hands. Angular momentum is conserved. Kinetic energy is not conserved. Work changes kinetic energy. Why don't I just do a calculation of the centripetal force when the masses are extended and multiply by the distance traveled by the masses inward? We can't do that because the force is not constant, and it's not an easy calculation. The force is variable. The centripetal force is variable. Centripetal force is m mass times v squared divided by r, and the r is changing, the v is changing. It's not a simple calculation, so I'm not going to do that calculation. I'll just give you the reasoning. Works has been done by Nate's hands on the masses, moving them towards the axis of rotation. There is an increase in the kinetic energy of the system. Well, I've got lots of other YouTube videos that are listed and grouped by topic on my simple website, gpclements.com. You click on links to get to the topic area of your interest, and then scroll down the list. There's a title. That title is a direct link to the YouTube video. You don't have to go back and search on YouTube for the video. You can click on my link. The annotation shows you how many minutes the video takes and to view, and also describes the calculations or content of the short lectures that I put on there. All this content is free. You're not allowed to resell it, but you do not give me your name, you do not give me your email address or any other information. And this simple website does not put cookies on your computer. So hope you keep working sample problems in physics, and ask your instructor if you have a question.